Hey guys, in our vote for our next video topic, hydrogen telluride emerged as a winner with a twofold advantage. So this video is all about it. This small piece is a monocrystalline tellurium. It's a low-toxic rare semimetal. While pure tellurium is a low-toxic substance, in this video I'll showcase hydrogen telluride, one of its most toxic compounds. When zinc interacts with tellurium, it forms zinc telluride, a zinc salt of hydrotelluric acid. Reacting with aluminum telluride is produced. This crystalline powder is zinc telluride, which, due to the prolonged storage, has taken on a grey color despite its expected reddish tint. This chemical is quite expensive, and the yield of hydrogen telluride using zinc telluride is quite low. For this video, I had to spend over 200 grams of zinc telluride to show you just a couple of reactions with hydrogen telluride. To prevent decomposition in humid air, I passed dry argon through this glass equipment to protect against oxygen. Adding zinc telluride to hydrochloric acid initiates the formation of hydrogen telluride. Afterward, I turn on the argon flow, and after a while, you can attempt to ignite the gas emerging from the glass tube. This is precisely the color that hydrogen telluride burns. When the light is on, you'll notice the tip of the glass tube covered with a layer of tellurium. By the way, tellurium plasma has a similar color. Here I introduce liquid oxygen to demonstrate the combustion reaction of hydrogen telluride in a pure oxygen atmosphere. Lead nitrate turns black upon contact with hydrogen telluride, forming black lead telluride on its surface. The lead nitrate solution has the same property. It's interesting that sodium peroxide, which easily ignites hydrogen sulfide, fails to ignite hydrogen telluride. The more active potassium superoxide cannot ignite it either. But then hydrogen sulfide through concentrated nitric acid results in the formation of large amounts of nitrogen dioxide. Here we can observe the formed sulfur at the tip of the glass tube in contact with nitric acid. A comparable reaction can be observed with hydrogen telluride. To avoid sacrificing lighting, I protected our synthesis equipment with foil. The resultant tellurium dissolves in nitric acid, forming tellurium dioxide. If we replace nitric acid with hydrogen peroxide, the tellurium formed during the reaction will not dissolve. This allows us to observe a significant formation of elemental tellurium. Now it's time to liquefy the hydrogen telluride. The hydrogen telluride formed during the reaction of zinc telluride with hydrochloric acid will be entrained by the flow of argon into the drying tube with calcium chloride. Then it will enter the cooling mixture where only hydrogen telluride will condense, while argon and traces of hydrogen chloride will evaporate. Overall, I shielded everything from light and started the synthesis. After spending about 200 grams of zinc telluride, I managed to concentrate only a little more than 5 milliliters of gas. Though transparent now, it will quickly turn black due to rapid decomposition. According to the reaction equation, 1 gram of zinc telluride should yield about 670 milligrams of hydrogen telluride. You can also see solid hydrogen telluride here. When I attempt to ignite it, it burned with a pale green flame. Liquid hydrogen telluride undergoes photodissociation, and when illuminated, the rate of its decomposition increases quickly. Look how an initially almost transparent liquid rapidly turns black. It appears to be boiling, but now its temperature is much lower than its boiling point. The actively released hydrogen resulting from photodissociation creates this effect of hydrogen telluride boiling. Synthesizing such a small amount of liquid hydrogen telluride consumed a lot of time and resources. Therefore, I wasn't able to conduct various experiments with it to select the best reactions for a video. I opted for the reaction with manganese heptoxide, knowing that liquid hydrogen telluride would definitely react with this substance. This ensures that I will not waste such a hard-earned and valuable liquid. Before pouring liquid hydrogen telluride onto manganese heptoxide, I cooled it considerably. Despite this, it still seemed to boil, but in reality, it decomposes into hydrogen and tellurium. Here I intended to add liquid oxygen to the remaining hydrogen telluride, but due to the small amount, I didn't have time to do this. After all the gas evaporated, only elemental tellurium remained in the test tube. Thanks for watching, guys, and thank you for your engagement through likes, comments and subscriptions to the channel. I really enjoy creating these chemical videos for you. If you have the opportunity to support me financially, please do so through Patreon or crypto. This can significantly reduce my financial burden on producing this chemical content. See you in the next video.